good afternoon and welcome to our presentation. I will introduce this work together with Alexandre Lucas from InescTEC. My name is Antonello Monti from RWTH Aachen, so I'm from here. And topic is interoperable open source tools so actually CUPID is the product here, controllable unit protocol interface for there, but come from the results of a European project called InterStore, that this longer acronym, interoperable open source tool to enable hybridization, utilization, and monetization of storage flexibility. So background, as I said, because we are still running the project, developing a solution for hybrid storage systems, and in that context, we focus as one of the key innovations of the project to have an open source implementation of the IEEE 2030.5, and so that's what then we isolated from the project, packaged as a project, separate, and brought to the Linux Foundation. But before, let me step back and give you a little bit of flavor about the project so that you see where we came to what we have. So the InterStore project is part of the activity of the European Commission related to a set of legislation, the EU Green Deal to begin with, but the more recent Repower EU. And so the idea was that this call, specific in this large program, was targeting the idea to prepare the European market and particularly the inverter manufacturer for the adoption of the protocol 230.5. And we see this as a way to achieve a higher level of interoperability, as I will show you also with the general architecture that we built, and facilitating beyond what the scope of the project was initially, that was focusing on the storage and hybrid storage, actually what we developed as a broader set of applications, basically, you may say any distributed energy resource. And we want to acknowledge here, as I said, there are two partners represented with my university, RWTH Aachen, and InescTEC, but we had more partners involved. For a duration of 36 months, we are going to have the final of the project in a month, if I remember correctly. And we had a budget of more than 4 million that went into these activities. And yeah, you see the list of partners. I want to mention for Centro Jülich because the representative from the project is here. And also engineering that is there. Okay, they were involved in the project. What we did was is well represented in this slide. So we had some pillar describing our goal. First of all, to develop everything as an open source interoperable software kit. And we want to be able to bring in the new generation of energy and flexibility management system. At the same time, we want to be able to link to a broader activity of the European Commission, which is the development of a common European energy data space. And so the solution in our architecture is compatible also with that. You can hear more about it tomorrow when another sister project that is the OneNet will talk about the data space connector that is named out of the OneNet project, but is also being partly developed here. Last part is the flexibility, hybridization, and monetization, which we're also able to test in 4 pilots with a variety of use cases. If you're not familiar with the European project, this is a typical structure. I was discussing this over lunch with some colleagues from the US. So yes, we have to do research. Yes, we do report, but basically every time we have this name, innovation action, we have to go to the real field and do something that works. And so whenever you see that label in the European project, you can be sure that it's delivering also some concrete, usable results. The vision on this flexibility service, here are the actors that are involved. Our focus is here So particularly we expect then the key actors, and also in our project are the one dealing with that, are possibly aggregators that are bringing together a set of resources. They want to be able to offer that either to the distribution system operator, either to the transmission system operator, depending on the kind of market they are targeting with the flexibility. But at the same time, the idea was to build, as I'll show you better, zooming in here, an architecture that creates a high level of interoperability among several possibility of resources. This is described in two parts. The first one is here. You see, first of all, we have been also linking to other LF activities and also previous activity like the European Union, like the Interconnect project. It was previously led by InescTEC. And the idea is to have the 2030.5 data bus as the interoperability element, with one element of novelty respect to other implementation 2030.5, because we implemented 2030.5 over NATs, and then enabling then the possibility of multi-to-multi type of communication, which makes the protocol much more flexible than the classical implementation. And here is example, a variety of resources that could be there, and the aggregation platform or energy management system on top that then will be the one in charge of interacting. All that get organized in this vision, also built on the shoulder of previous activity where the partners were involved, and so that we put our work more in the context of bigger digitalization type of activity, and particularly also here is where you can see the connection also to the data space element. Concretely, when you look at the content of CUPID, there are three fundamental tools. The first one, maybe I would say the most important, is the client server for distributed energy resources. So we have available both a client library and a server library, in any case with native messaging over NATs, as I mentioned before. And we see that as one of the major value of our implementation, because makes the use of this protocol more flexible than other previous implementation. The second important point is that very likely if you go in the real life, and that was actually our situation, there may be devices that have not been built to be 2030.5 compatible. And so a very important part of our vision has been the developing of a legacy system protocol converter, so that even devices that are not native 2030.5, thanks to our library, get wrapped around a protocol converter that makes them compatible with our data bus, so that interoperability is anyway achieved. And again, later I have a couple of examples. That was actually the situation that in our field tests we face in several instances of the components we integrated. So having then the chance to show in the real life that this vision makes sense beyond just the theoretical implementation. And last but not least, oh, sorry, here some more element on the legacy converter protocol. But the third part is also that to make sure that at the end you can be sure about what we are doing, we also put together a testing procedure and software tool, so that before you bring components, you can verify the compliance with a set of automatic tools, so that we have the possibility to have an automated testing before connection to the platform. And we have a set of test cases that have been covered. I think this doesn't cover all the possible situation in 2030.5, so this is a part of work that can be extended in the future. But we, thanks to the variety of use cases that we had to cover, we had already a pretty good list available. As I mentioned, very important is that it was not just work in the lab. but we had 4 different experiences in Italy, Germany, Portugal, and Austria. In Italy, this was in cooperation with Enel on their e-mobility laboratory. Then in Germany was the research center in Jülich, Forschungszentrum Jülich, which is developing a smart campus. So then integrating a variety of assets in our campus and developing their own EMS and making sure they become, I think they have, if I'm not wrong, the target to become a zero impact campus in the future. So that's a key asset in achieving the goals. Then in Portugal was a test related again to e-mobilities. And in Austria, we had a partner, Cybergrid, which is basically providing a platform for aggregation. So they also had the chance to try on the real life deployment of their platform. To orthogonally say to the location, definition of use cases. So you can see that thanks to the variety of field tests, we had a chance to try a variety of situations. And you see that in several of the use cases, the protocol converter is part of the story, so that we had a mix of components in that specific real-life deployment of 2030.5 ready and non-ready. And then on the right, the use cases, flexibility, market monetization, use case on energy community, grid supporting storage, frequency service, this something innovative, looking at providing services also related to inertia by electronic devices, so virtual inertia principle, hybrid floating storage flexibility monitoring, management of battery systems for node capacity increase, adaptive storage management for autonomous grid operation, home management system, and cluster of e-charging. These crosses here represented out of the use cases, which use case was tested in which field test, and each field test, as you can see, had more than one use case contemplated. So they had a chance to try a variety of situations in real life, real data. And then I have a couple of schematics of use cases. And you can see, for example, here, this is in reference to the platform Forschungszentrum Jülich. So we have a device side, something that was actually ready to talk Modbus TCP. Then we put in the middle legacy protocol converter, and then we are able to use as data bus the 2030.5. In this other, oh, sorry, this doesn't change. This other situation, again, we have the role of, we have a battery systems, in this case, capable through the, to adopt directly the 2030.5, but also some other connection based on Modbus TCP, and again, the need of protocol converter. That's first for an EMS implementation. Then we have here another instances in which we need to put the protocol converter, again, for a set of battery systems that were integrated. Here, this was the platform from CyberNOC, is the one from Cybergrid, which is capable of talking 2030.5. So they embedded our solution in their platform, but they may have external devices which are not ready, so they may need as well the protocol converter. And last but not least is the Italian use case. In that case, they were using MQTT and JSON as a protocol. And then again, thanks to our adaptation, we are able to switch to the 2030.5. So as you see, a variety of condition and situation, variety of devices, but always at the end, the possibility to create this common interoperable bus on 2030.5. With this, I move to Alexandre that will take over for the second part.
Thanks, Antonello. My name is Alexandre from InescTEC. We are technical coordinators of the project. So by now, it should be clear that the main outputs of the project and what we are proposing in Linux Foundation are the legacy protocol converter, the native library that enables the client server to use the NATs, and the testing procedures. Now, and it should be clear also that the powerful combination of what we are proposing comes from the IEEE 2030.5, and I know that some colleagues here are knowledgeable on SunSpec, IEEE 2030.5, I was discussing this before, with the NATs, because the NATs, the original version comes with the REST APIs, and as you know, REST APIs is synchronous, it can fail, and with the NATs, it's very fast, it's asynchronous, and it enables and unleashes many use cases because of the many-to-many features, many-to-many communication features. So just imagine, for example, the Modbus communication where you have this master-slave relationship. The slave or client cannot communicate with whoever he wants. So here, with the NATs, you can have many-to-many communication. Think about the edge intelligence, the edge devices, the orchestration between so many platforms and resources that we can have. Optimization, AI being distributed there in so many Raspberry Pis and NVIDIA components, etc. And so this is what we are proposing. Regarding the versions now that we have available, so far at this moment, we have the 1.4 version of the legacy protocol converter, so I invite everyone to visit our webpage. You can find it easily on Google. You can visit, you have there actually the links to our Docker Hub, to our GitHub. And so this version is the most up-to-date, on which we have integrated the lessons learned from the pilots. So we had some synchronization issues that were brought up by Julius, for example. We had some file size, the log files generated by the legacy protocol converter. We solved those issues, so this is up to date. It's not an expression of intent. No, this is work done and tested, and it works in 9 different use cases, as Antonello explained. Also, regarding data space, I mean, in the inspiration, in the flavor of the Linux Foundation, this is also being advertised here in this summit. We have so far the 1.3.2 user interface of the data space connector developed by our colleagues from engineering here. It features the blockchain option to register the file exchange. It features the actual user interface, and it features a push mechanism of data. And so during or since the last meeting that we had with the Linux Foundation, we've developed, and we are almost done with all the demonstrations in our project, all except one. And not only have we monitored many assets and variables, we've also controlled. It's not a question of monitoring, we are controlling. We deployed the legacy protocol converter, the native libraries, we've tested and used the procedures. We've done this with platforms, energy management systems, and we are proposing 4, and the actual devices. And also we tested this performance in very severe lab conditions using a real-time digital simulator with our colleagues in Spain. Just to tell you a bit about the engagement that we've had so far. These are only data from our Docker Hub because we don't have visibility in GitHub. But we've had more than 1,000 downloads already with the legacy protocol converter, and also the other tools have had some engagement as well so far. So I invite you also to take a look at the GitHub, not only, or the Docker Hub, not only at the GitHub. Regarding performance and some numbers to go with it, some initial numbers that we are now assessing, the KPIs that come out of the demonstrations. In terms of communication speed, using both the IEEE 20.5 and the NATS. We've had under 100 milliseconds, actually much lower with the colleagues from Spain, around 50 milliseconds. So this puts this combination of the IEEE 20.5 and the NATS as the candidate, as an ideal candidate for very fast grid service provision, where it cannot fail because it's an asynchronous wave communication. It can handle many communications at the same time. And so for critical infrastructure, critical services, this is the ideal candidate. And it's CPU friendly, let's say, something that maybe MQTT can have its challenges. We've tested multiple number of distributed energy resources. We are monitoring more than 37 assets and successfully tested with the energy management systems 21. So just to give you an idea, if we aggregate, so the overall power of the hybrid energy storage systems that we are using as examples of distributed energy resources, it's just over 4 megawatts. So it's not a tiny thing. We are aggregating quite a lot of power here. We have put out during the project in the beginning of the year or just finishing last year, I think, our white paper. And so here I would invite you to take a look for those maybe who are starting to look at the IEEE 20.5 and what it can do for you. It's a very informative document, straightforward to read, to understand. Here we provide policy recommendations. We make a comparison with other standards and protocols, IEC 104, IEC 61850, MQTT, Modbus, OpenADR. So we provide this comparison. I think it's quite comprehensive. And in the end, we want to move forward and look at adoption. And we question why is this being adopted in California and Australia, and why does it lag to start being implemented here in Europe? And I think it will gain some traction, especially with the developments that we've ensured here in this project. And after the project InterStore finishes, this will be the main stage. This is the reason why we chose Linux Foundation for Energy to disseminate the developments, but also to create a community where we can further develop the legacy protocol converter and other developments associated to it, because so far we've ensured the conversion from Modbus and MQTT to IEEE 2030.5. I mean, but many other cases and many other conversions can be ensured. So we hope to get your engagement here. This is the GitHub URL that you can follow. And if you happen to be around Brussels on the 25th of November, we will have our final event. And also, it's a hybrid event. So if you are not in Brussels, please join us. You can register in our webpage, in the project's webpage, very easy, very fast, where we will be able to talk about all the developments in the spirit of the Linux Foundation for Energy open source. Because not only these models were developed, but also we put forward actually work by InescTEC for valorization cases for the data spaces. We have a hybridization tool. So all of this is open source, hosted by our own open source GitHub, and also present in InterStore's GitHub. And yeah, and so this is the status. I mean, we have very little work now to finish in InterStore, just one demo still running. We're about to calculate and finish all the KPIs. And in CUPID, so far, we have our partners, so RWTH, InescTEC, CyberGrid, and Sunesis as the technical board to move forward and to engage with you. Thank you. We have some time for questions, though. Please, yeah, Alberto.
No, it was our approach to address the code.
And which kind of asset did you interface? Also residential devices?
Yeah.
I think, Alexandre, you touched a bit at this point. While you were presenting this, came to an mind that IEEE 2030.5 is not so common here in Europe yet. While, for example, I see a lot of propagation of OpenADR, for example.
Right.
So
They're not the same thing. So that's also what is in that white paper. So the 2030.5 is a control type of protocol. 2030. Well, OpenADR is flexibility management. It's a different concept.
How do you see the future for the 2030.5 in Europe? Do you think that is getting traction or is something broken?
I think the use cases. I think the use cases are there and start to pop up, and especially in the Horizon Europe calls that are yet to come, that start requesting edge intelligence orchestration between many EMS platforms and intelligent devices, inverters, and so on. I think it will have the floor for this deployment and further enhancement of these tools. Just to answer about the OpenADR. OpenADR has a hierarchy. It comes from top to bottom. The IEEE 20.5.NATS couldn't care less about hierarchy. It's many to many. It's a published subscription approach, and so this is the brilliant part of it. But the call text did mention interoperability, and actually the sister projects that we have, other two, FlatChess and Parmenides, they were pushing for a more ontology-based approach for interoperability, where the IEEE 20.5, this is a dictionary hosted in the devices and in the platforms themselves. We don't need internet, we don't need to point to ontologies, we all speak the same language. And I think this is, many things can be said, and we've promoted this discussion in our workshops, in InterStore workshops that we've been having with other partners and within our stakeholders community. We'll have again our next meeting next week about this ontology or dictionary-based interoperability approach. And many things many discussions have emerged, and we're not sure about who must win, or if at all, or if they are complementary depending on the use case. So we were part of IntNet, and this was very good to discuss. Thank you, guys. We finish?
Yeah, I think I was.
Thank you so much. Thank you.